Hello, my name is Jim Schall and I'm a consultant to the Federal Highway Administration on highway drainage issues. I teach several of the Federal Highway Administration training courses on highway drainage and have been practicing in this field for over 40 years now. The purpose of this video today is to look at some of the drainage related issues you might consider in an initial scoping level investigation for a highway drainage project. Before going into the field, you should have already reviewed all available information on drainage, information that might be shown on the as-built plans, information in a drainage report, perhaps maintenance history, any inspection reports, and possibly any citizen complaints about local drainage in the area, as well as any geospatial data. The Federal Highway Administration video on field preparations and data mining provides good information and insight on how to collect some of that information, including the geospatial data that you can find online. As we start the video, one of the first things we'll want to talk about is good documentation in the field. When you're out in the field, you want to be documenting what you see, making notes. That could be as simple as in a field book and a camera, but perhaps more ideally using a tablet so that your notes and any photos and video you take can be geotagged to the location you're at. Finally, whenever you're on an active roadway, be aware of the safety hazards and the mitigation of those hazards that you should take, including the use of personal protective equipment consistent with your agency recommendations and requirements. So let's begin by looking at some of the typical roadway drainage elements on a highway project. As we look at the roadway itself, the water coming off the pavement enters into the shoulder area and then flows into the ditch. If this was a divided highway, we'd have both a roadside ditch and a median ditch. This is a 2-lane, we just have a roadside ditch. Starting up on the shoulder area, we'd be looking for any signs of erosion, any rilling in that surface, any areas where the vegetation isn't doing well, where the slopes might be too steep. In winter climates where there's a lot of sanding in the wintertime, you may have some sediment that's accumulated, some of the sand along that shoulder area that can impede the free movement of water off the pavement from the cross slope and the longitudinal slope of the roadway. If that's a concern or something you note, might be evidence of a piece of roadway with a lot of wintertime sanding or inadequate maintenance, something that the hydraulic engineer would want to know about in terms of how they analyze the drainage patterns. As we get into the ditch itself, we'd be looking at any erosion in the ditch, any sediment deposition, any areas where there's debris collection that might impede water movement. This ditch is fairly low sloped. It's very well vegetated. The front and back slopes are good. We don't see any signs of erosion or problems here. But if you're in a steeper sloped area, you could have some erosion of the invert. You might have some revetment or some channel lining materials. You might even on a very steep area have some rock check structures that are there to try to control the erosion and reduce the shear stresses that are causing lining failures. If that exists, make a note of those features, document it with photography so that you can properly plan for future changes and improvements in that ditch. As you come into a town or city, any urban corridor, you're going to transition from the rural highway section with shoulders and ditches and median ditches to a more urban drainage situation with curb and gutter. That introduces some additional elements that you'll want to note and observe as part of your scoping level investigation. The different types of conditions you'll see is the type of curb and gutter section, the type of inlets. In this location, we have a straight gutter section. A straight gutter section has a cross slope that's the same as the pavement slope. Another gutter type is a composite gutter section where the gutter slope is steeper than the pavement. That's done for hydraulic reasons. Hydraulic Engineering Circular number 22 by the Federal Highway Administration provides insight and guidance on the various urban drainage design features that you'll see in an urban corridor and discusses the different types of gutters and grates that are available. This gutter is in good condition. There's no evidence of deterioration. There's no evidence of sediment deposition or debris problems. The gutter leads to a grate. There's 4 different categories of grates described in HEC 22. It could be a curb open inlet. It could be a grate inlet. It could be a slotted drain, or it could be a combination inlet. This inlet is a combination inlet. We have both a curb open and a grate, and this grate is furthermore a curved vein inlet where the veins help turn the water into the catch basin as it's coming down the gutter. You'll want to identify the type of inlet you have, verify it's part of your standard plans or the inlets that are currently in use by your agency. If it's not, you want to get some measurements and photographs of that inlet, whatever it is, the dimensioning on it, the bar spacing, the open area, so that that inlet can be identified, which will be necessary for any hydraulic analysis done evaluating the interception capacity. As we continue down the highway, we'll see additional inlets. This inlet is downslope from the first inlet we looked at. It's the exact same inlet. It's a combination inlet, curb open with a curved vein grate inlet. But notice the deposition in the gutter at this location, and the grate itself is completely plugged. So this inlet and this gutter section are not working as well as the first one we looked at. Could be because of heavy sanding along the roadway in this area. Could be inadequate maintenance. It could be that the gutter slope is too flat to keep the sediment moving and we get the deposition. Those are observations you might want to make so that the hydraulic engineer can evaluate the drainage conditions in the gutter and decide if the longitudinal slope is adequate. All these inlets will connect into a storm drain system. The storm drain can be identified in general by the location of the access holes. And what we want to look at on the storm drain is whether or not there's any cracking along the pavement surface along the alignment of the storm drain based on the access holes. Look for any pavement depressions that might indicate fill problems around the storm drain pipe or possibly even collapse of the pipe. We don't see any of that evidence here. This appears to be in good condition. If you do suspect a problem, don't attempt to open the access hole cover and climb down into the storm drain without taking adequate confined space precautions. As you continue along your highway project doing your scoping level investigation, you're going to come upon some various cross drainage structures. Could be bridges or culverts. Bridges should have enough information from the inspection reports that are required as part of the NBIS that you would have found in your pre-field investigations in the office. Culverts you may want to spend a little more time on in the field, so you'll be looking at the conditions of the culvert and the roadway over the culvert. As we look at this particular crossing, this culvert crossing, we see no evidence of any fill material problems that might show up with depressions in the pavement or the guardrail misalignment, deflections in the guardrail that would suggest problems with the fill material. So let's go down below and see what we see on the barrel itself. Okay, we're down here now at the channel approaching the culvert. We're going to begin looking at the culvert in more detail, going through some type of culvert assessment procedure. That usually entails looking into the barrel. That can be done with what we call an end-only inspection. If you see some problems or you can't see far enough into the barrel, you can do a ROV, a remotely operated vehicle inspection. And on larger barrels, you can sometimes walk through the barrel. If you want to do a person entry inspection of that sort, make sure you follow all appropriate confined space considerations. The assessment procedures you do on a culvert, if you don't have a state standard, there's a couple of guidelines that might be helpful to evaluate the factors of interest, which will include the structural condition of the barrel, the soil conditions around the barrel, and the hydraulic conditions of the barrel. One option is the Federal Highway Administration Culvert Inspection Manual. If you want more information on that particular method and procedure, contact a Federal Highway Administration Resource Center hydraulic engineer. Another option is the AASHTO Culvert and Storm Drain System Inspection Guide. Both these methods are meant for rapid assessment to allow you to do a very quick assessment of culvert condition and evaluate what's going on, typically on a 4-factor scale: fair, poor, good, fair, poor, and critical. You rank those factors, and then that allows you to understand whether or not the culvert is at risk, whether it needs to be some maintenance work or a full replacement or lining done. The other factors that you have to consider when you're looking at culverts is the issue of aquatic organism passage. That's a factor, AOP design, that's gaining interest nationwide. Historically, a lot of our culverts were smaller, that we did intentionally to make use of the available ponding, but that creates what we call passage barriers for aquatic organism passage, fish and other aquatic organisms that use the riparian corridor. Those passage barriers can include things like high velocity flow through the barrel, shallow flow depths. You could have debris blockage at the upstream end, so even if, say, a fish got through the barrel, they couldn't continue into the upstream channel. The concern is, from the resource agencies and biologists that are involved with this type of business, is our culverts create a barrier. They break the ecological connectivity between the upstream and downstream channel. So if you have a stream channel where aquatic organism passage is a concern, you're going to have some additional design standards and criteria. There'll be some additional factors you want to look at when you're in the field doing your scoping level investigation. So contact your resource agency for information. If you don't have guidelines, design practices that they recommend or that you're currently following, the Federal Highway Administration has a design practice. It's in the Hydraulic Engineering Circular number 26. It's a stream simulation method. The U.S. Forest Service also has a design practice. It's what we call stream simulation design. And the intent of that is that you make the barrel itself look like the upstream and downstream channel that allows the ecological connectivity and the movement of aquatic organism passage in a more free and unrestrained manner. That might be a concern. If it is, like I say, you'll want to investigate that in more detail. For today, we're going to look at just a quick assessment of some of the hydraulic factors of interest, which will include both the channel and the culvert that might be included in whatever assessment procedure you're following. We start by looking at the upstream channel, and what we see in this location is we have a little bit of an incision going on. We see some bank sloughing, some failure along the bank line. There's good vegetative cover, but there's a little bit of erosion going on. The channel is meandering, which a lot of natural channels do, but as a result of that meandering action, we see as the channel approaches the barrel, we have a skewed alignment. That's not a good situation for hydraulic conditions at a culvert entrance, so you'd want to make a note of that. All of this can be photo documented. We recommend that you take at least 7 photographs when you're doing a culvert assessment. Starting up on the roadway where we began, a picture of the conditions of the roadway and the guardrail, a picture of the upstream and downstream channel. That could be from the roadway vantage point, or it might be once you get down nearer to the barrel. You'd want a picture of the entrance condition and a condition of the outlet condition that documents any head walls or wing walls or other appurtenances, safety grates, whatever there might be. And then a close-up looking into the barrel from both the upstream and downstream end. So a total of at least 7 pictures. More is usually better, particularly if it's a complicated hydraulic situation. Those pictures will help the hydraulic engineer understand the best way to analyze that culvert crossing. So let's go up a little bit closer where we can actually look at the barrel and talk about some of the assessment factors you would typically consider. We're here at the entrance to the culvert. You'll be going through whatever assessment procedure you're following to identify the condition of the culvert, the entrance configuration, the types of conditions that exist. Certainly one of the first things you'd want to do is verify the size of the barrel, the shape and the material type, and make a note of that. This is a 7-foot corrugated metal pipe culvert. It's in fact a structural plate culvert. It's been assembled on the job site in pieces. That's what is a typical larger barrel construction method. You want to verify the entrance configuration that exists. That's important for hydraulics and the behavior of the culvert hydraulically. This is what we would call a thin edge projecting inlet. If you need more information on the types of inlet configurations that are used on culverts, the Federal Highway Administration Hydraulic Design Series number 5 on culvert design provides a lot of good information. In addition to thin edge projecting, where the barrel's projecting from the fill, common entrances include mitered to the slope and a head wall with or without bevels and with or without wing walls. So those are some of the more common types of entrance configurations. We have a thin edge projecting inlet that is, in fact, as you can see, has been damaged. We think part of that damage is probably due to the steepness of the fill around the barrel as it projects out of the fill material. That's caused problems with the riprap staying in place with the fill material. We see some sloughing of the bank line on the far side. Those are issues that you would want to note in your report. Perhaps this should have been a longer barrel to allow the embankment to be graded at a more gradual slope. Perhaps a head wall would have been a better choice at this location. Factors that the hydraulic engineer will want to know and consider if they're looking at changes to this culvert or the entrance configuration. You'll also want to look inside the barrel and see what's happening both with the alignment through the structure, if it's any deflection, any alignment issues, failure starting to occur, any joint separation. You'd want to look at the condition of the invert of the barrel. In this one, we start to see a little bit of rust. Looking down into the barrel, I saw no evidence of perforation of that barrel yet, but it may not be too far from that point, at which point your lining methods and replacement methods change. You're probably unable to line, you might have to do a full replacement. So those types of information, that knowledge is helpful to the hydraulic engineer looking at what to do with this culvert that is showing some signs of distress that probably will need some repair, relining, or replacement in the future. So let's go to the downstream side and see what we see at that location. Okay, at the downstream end of this barrel, we see basically the same culvert that we saw on the upstream side, a corrugated metal structural plate culvert. That isn't always the case, it's typically the case, but if this roadway had been widened in the past, it wouldn't be out of the question that you might see a different culvert shape or material type or size at the downstream end. So you'd want to document that so the hydraulic engineer knows that the barrel size has changed. But in this location, we see the exact same barrel. One thing we do notice in this location is we have a perched outlet, meaning the barrel is higher than the downstream channel. We also see a very large scour hole that probably developed during a high flow event, indicating potential risk of that culvert undermining at the outlet. We don't see any of that yet at this structure. The riprap is still adequately protecting the outlet. There's no sagging or potential separation at the outlet. But the perched outlet is in fact a aquatic organism passage barrier. So if that was a concern at this particular crossing, that would be something you'd want to note. The rock around this outlet, as you look around at the different types of rock that are present, there's different sizes, there's some different coloration on some of that rock, suggests this has been an ongoing problem. There's been ongoing maintenance, additional rock brought in over time to try to protect the embankment fill and the barrel itself. So again, something you'd want to note is as part of your scoping level reconnaissance. And then the last thing you want to look at is the tailwater channel leaving the culvert. The tailwater hydraulics are important to the hydraulic engineer in terms of evaluating how the culvert performs and what the headwater conditions look like. If the channel is fairly uniform and stable downstream of the barrel, that analysis is pretty simple. If the channel is very non-uniform, as we see here, where we have a scour hole, we have some bank line collapse, we have a meandering channel that's incising, a lot of variability, that calculation becomes more difficult. So additional documentation on the tailwater conditions, some additional photography would be warranted at this site. As you look at the scour hole in more detail, It would be helpful to estimate the size of the hole if you can, the width and the length, and if you can see the invert, to estimate how deep it is. And further down into the tailwater channel, estimating the size of that channel. That will be helpful for the hydraulic engineer who's working on the tailwater channel conditions. Knowing that this might be a culvert where there will be some repair work, perhaps relining, perhaps replacement in the not too distant future, as part of your scoping level comments and review, you might want to take a quick look around and see if there's a better location for construction access. Is the upstream side better than the downstream side? Can you get equipment down here to the channel? Are there suitable places for staging operations? So that as you begin to develop the project in more detail and you start thinking about the different elements of the design that might be required, you have some ideas of how you might go about that design and that construction project. As you continue along your highway project doing your scoping level investigation, you're going to encounter additional culvert crossings of varying sizes. At this location we have a smaller 36-inch RCP, reinforced concrete pipe, with a standard end section. This is a newer culvert, looks to be in generally good condition, but that's not to say all the problems we observed at the larger culvert earlier in the video, the issues with the inlet conditions, the issues with the barrel deterioration, the concerns at the outlet with the scour hole and the perched outlet, couldn't exist at a smaller barrel. In fact, they often do have the same problems. But this culvert is in generally good condition. You would go through the same assessment factors that we talked about at the larger barrel, evaluating culvert condition, but as our initial reaction looking at it is it's in good condition, with just one exception. We see at the entrance to the culvert here, the rock that was placed, the riprap, the revetment to transition out of the ditch and into the barrel is probably mounded higher than we'd like to see. I doubt that it was shown that way on the construction plans. It's how it got built. That would be an impediment to the free-flowing movement of water from the ditch into the barrel, something you'd want to make a note of and be aware of at other culvert installations. At the downstream end of this barrel, we see the same barrel size. We see another standard end section. One thing we'll want to do when we're doing an end-only inspection is take a look inside the barrel and look for any sediment deposition, any debris collection, any joint separation, particularly on an RCP pipe, any deflection in the alignment. So as I take a look into the barrel, everything looks good. The barrel's in good condition. There's no sediment deposition. There's no debris collection noticeable. At the outlet, we have more riprap, more revetment to transition into the downstream ditch. This rock is in good condition. Unlike at the upstream end, it's properly placed. There's no mounding of the rock above the channel grade or the culvert invert. This is what we like to see when we're placing riprap. We also have a corrugated metal pipe, CMP pipe, with a metal standard end section that's bringing the drainage across the county road here. And that too is a fairly new structure. It's in good condition. If I were to take a look inside this one, I see much the same. A nice straight alignment. There's no evidence of invert deterioration like we saw in the bigger barrel earlier in the video. There's no sediment deposition. So both these structures are performing as we would expect. There's really no issues to note and no problems at these particular culvert crossings. As you continue along the highway on your scoping level investigation, you continue to make notes and observations and take photography on issues related to drainage, the shoulder conditions, the ditch, the median ditches, the culvert crossings, any of the curb and gutter issues that you noted, following the suggestions that have been provided in this video. You'll find as you get into the project deeper and you're developing some of the elements of the scope of work and the project design, additional field visits will likely be necessary. Whenever you return to the field, make sure you follow appropriate safety precautions consistent with your agency's recommendations. Thank you for your time today, and I hope you found this video helpful.